Now, a few miscellaneous topics related to observing. So first, the Earth's atmosphere. Why is the sky blue? Why are sunsets red? And then we'll talk about the advantage of using space telescopes to observe other wavelengths of light than visible light. So why is the sky blue? Why are sunsets red? These two questions are connected. So here's a photograph of the sunset. At sunset, do you think the sunlight has to go through a lot of our atmosphere, more atmosphere, compared to if the sun is at noon on our meridian? In which case will the sunlight have to travel through more air? And you should say sunset. The sunlight has to travel through the air for a longer length at sunset, the sunlight does, compared to at noon. It turns out that as light comes through our atmosphere has an effect on it to remove blue light from the beam. Removes blue light from the beam. And red light is more able to get through this thick atmosphere path length and come to us. So we see red sunrises, we see red sunsets. At noon, the sunlight is going through a thinner length of air, and we lose some blue light. That's what creates the blue sky. The blue light is scattered out of the sun's beam into different parts of the sky and comes to our eye. But that blue light came from the sunbeam itself, and there's less blue light left in the sunbeam. This is called Rayleigh scattering. The Rayleigh scattering effect, it turns out that our atmosphere, molecules in our atmosphere will scatter blue light better than they scatter red light. So the blue light from the beam gets scattered away from the direction the sunbeam is traveling. The red light is not scattered as much, so we end up subtracting blue light and green light from the sunlight. And at sunset, its effect goes more strongly because there's more air to travel through. So at sunset, we're just left with the reds and oranges. Makes a pretty sunset, and there's a bit of physics here. When the sun is high in the sky, this blue light is scattered all around the sun on the sky and makes our sky blue. It's a scattering of light that makes the sky blue. And at sunrise and sunset, the sunlight that comes to us travels through a great distance of air, and the blue light is removed from the beam of light coming towards us. It's scattered away. So let's go on to a new topic here. And now, observing the universe at wavelengths other than visible or radio is very important to astronomers. Astronomers would like to get a lot of information about objects at different wavelengths because those different wavelengths have different spectral lines. They have different clues about the nature of the object being studied. So we need to go into space. We need to put the telescope in space to get rid of the problem of the Earth's atmosphere blocking things like ultraviolet and infrared, X-rays. So we have been doing this for a number of years, since the late 60s, putting telescopes into space, and they have provided astronomers with a great advance in knowledge about our universe. So an example of this would be the constellation of Orion, here on the left, using visible light, and on the right side, infrared light. And you can see that there's much different information here. There are big molecular dust clouds in the region of Orion where new stars are forming, and you don't pick that up with the visible image. But the infrared is very good at revealing where molecules and dust are located. Another example here with X-ray image, visible image, and an infrared telescope image. All of these are taking a look at the same object. But with the X-rays, we see very high energy, high temperature regions. With visible light, we see more ordinary black body type light and some emission lines. And the infrared again shows the presence of dust. And you can see there's some correlation of these objects in giving some element of the same shape in all three instruments. But again, different information can be obtained, the temperatures, presence of dust and gas. So it's very useful to astronomers to have multiple wavelengths of observation. It's a big motivation to put telescopes into space, so we don't have the problem of the blocking, the filtering effect of the Earth's atmosphere. The James Webb Telescope would be the replacement for the Hubble telescope, and it's going to be more of an infrared telescope than a visible light telescope. These are not wings, but shields against sunlight to keep the telescope at a low temperature. That makes it better for observing the infrared. It'll have a segmented mirror that'll be quite a bit larger than the Hubble telescope and gather more light. Future plans may build telescopes on the moon. It's a nice stable platform. Be dark for a couple of weeks out of a month. As it goes through the phases, we know that every part of the moon has 2 weeks of night and 2 weeks of daylight when the sun's above the horizon. But there could be materials on the moon that are useful for constructing mirrors and constructing observatories. So perhaps in the distant future, we'll have telescopes mounted on the moon. So that's our tour of the sky and tour of space-based telescopes. Keep reading and asking questions.